Okay, so as a reminder here, I've jumped all the way back to slide 2. Our purpose is to be able to replace getting values from the user with cin and the getFrom operator, and instead to use the getLine function so that we can more carefully analyze what the user typed in rather than relying on getFrom, which basically either succeeds or fails. And cleaning up after failure is very painful. So we are, now that we know how to do relational tests, equality tests, and logical comparisons, we're ready to get back to the string class now so that we can start working with and analyzing strings. So string is a standard class in the C++ standard library, and it provides both named and symbolic operators. For example, the plus symbol for string objects in C++ is concatenation, in the same way that the plus operator with str objects in Python is concatenation. These are referred to as overloaded operators because the plus symbol is already used for integer and floating point arithmetic. As I mentioned way back on slide 2, which by now you've probably forgotten, if you declare a string object and you don't specify an initial value, then by default it is initialized with an empty string. So it turns out that in many ways the standard library classes are better behaved than the low-level fundamental types. They tend to start out in some reasonable default state and don't always need to be initialized with some values. You can find out everything there is to know about the string class by looking at the cplus.com reference materials. All right, so we have been using string literals in our code already. A string literal is a sequence of characters contained within a pair of double quotes. We've used hello world and so on. When we write a string literal in code, that gets represented in memory as an array of characters with a null character stuck on the end. Now the null character, recall, is the character whose value is 0, and it's usually represented in code with the notation single quote \0 single quote. So when I write this string literal, hello new line, in double quotes, in memory that's actually stored as an unnamed array of 7 char values, which if I represented them individually in my C++ code would be single quote h single quote little e single quote, and so forth. Now, a string object can be initialized with one of these string literals. Let's take a look at an example program. I'm going to skip slide 17 for just a second. Here is a string literal being used to initialize the string object s2. All right, now I will back up and take a look at slide 17. When you write a string literal, as I said, you get this unnamed array of characters with a null character on the end. This is called a null-terminated array of char. And this is the old-fashioned and still used way that the C language and the C++ language represent a string. Notice that this is a string not in bold, okay? In bold, I'm talking about the C++ standard library string class. So in C++, to differentiate between the string class versus the old-fashioned kind of null-terminated array of char strings, we talk about these old-fashioned kinds of strings as either C-style strings or often just C strings. All right, so what I've done here on slide 18 is I've used a C string, that is a string literal in double quotes, which is represented in memory as an array of 6 chars, H, E, L, L, O, and a null char. I've used that C string to specify the initial value for the C++ standard library string object s2. When I run this program, s1 has not been explicitly initialized, but it is properly empty, And so when I display the contents of S1 in this C out statement, I get no output. That is, I get the string S1 colon space. Okay, here is a C string, S1 colon space, and in memory, of course, there's also a null character stored. So I get that C string printed out, S1 colon space. The null is not printed out. It just indicates where the C string stops. Then the contents of S1 is displayed, which is empty. And then finally, a new line character is displayed. And that causes the cursor to drop down to the beginning of the next line. In the second cout statement, we get S2 colon space from this C string. That is, from this string literal. Then we get the contents of the string object S2 displayed, HELLO, and then we get a terminating new line displayed as well. Okay, so that would be the output of our program. So the getLine function reads in one line of input from CIN, and the end of the line of input is marked by the new line character. So that line that gets read from this so-called iStream object, this input stream object, is then stored into the string object that's given as the second argument. And getLine is smart enough to take off, to eliminate the new line that's at the end of the string. So here we have an example program. Actually, let me move this example program over onto the other window, and I will pull up my Ubuntu screen, and let's go ahead and type this thing in. Okay, so the name of this file is string2.cpp. I have previous programs, but I don't yet have string2.cpp. I'm going to create that with vi. And I'm going to cut out a whole bunch of my typing here. Notice that I want to be able to use string objects, and I want to be able to use the getLine function. Consequently, I have to include the string header in addition to the IOStream header in order to be able to use strings and getLine. Okay, then we have our using namespace. And here now I have defined a variable, I have declared a variable called line, whose data type is string, and it's empty. So I don't need to specify an initial value for line if I'm willing to just have it be empty. I will then display a prompt to the user. And because I have not specified a new line at the end of this prompt, the cursor is going to just sit there after the colon and the space. I'm going to use getLine instead of CIN with getFrom to read from CIN the next line of text that the user types. And just to confirm that getLine is doing what I claim, I'm not going to try to analyze the line in any way. I'm just going to display it. You entered whatever the user typed. And recall that getLine strips off the new line from the end of the line. So I want to add back a new line to cause my cursor to drop to the beginning of the next line. And of course, I'm going to return 0 to indicate success. So there is my program. I'll save it with WQ and compile it. I wanted to call this thing string2.cpp, so let me rename with the move command string.cpp to string2.cpp. Here is string2.cpp, and now I'm going to compile it. and run it. So I'll run string 2. If I didn't mention before, the reason I'm typing the dot and the slash is to tell my Ubuntu environment which directory this executable file is contained in. And here's my prompt. Enter text, comma, and press enter, colon space, and notice that the cursor does just sit there after that colon and space, waiting for me to type some lines, some line of text. And I'm going to say hello world because I'm enormously clever, and then I'm going to press the enter key. Getline will read in hello comma space world new line. It will strip off the new line and it will store hello comma space world into the line variable. And then the second cout statement is going to display what I typed. It's going to display you entered colon space first, and then it's going to display what I typed, and then we add a new line at the end so that the cursor comes down to the next line down. Okay, so we are able to read a line of text from the user's keyboard through cin using getline. I guess on slide 22, my example run, I was just a tad bit more creative than hello world, but not too much. All right, now the string 3 example program I've already typed in. So let me just show you the string3.cpp code file, and we're going to use this to illustrate various symbolic operations that you can perform on strings. Okay, so I'm going to use more to display string3.cpp. In the notes, it extends across 3 slides. Okay, so there it is, and I'm going to compile this thing now. G++ -o string3, string3.cpp. Whoopsie, made a typo, so let me fix that. Alright, so int main, and recompile. Alright, so now it compiled successfully. Alright, so let's walk through this. Let me run the thing in my Ubuntu window, and we'll walk through and see why we're getting the output that we're getting. Okay, so in string3.cpp, we're using string objects, so we have both the IOStream and the string header included. We're also using our namespace standard statement. In main, I'm declaring and initializing 4 string objects. S1, which actually I haven't given any explicit initialization for, so it is initialized to be empty by default. And then S2 and S3 and S4, which are all initialized. And I'm just to remind you, using the 3 different possible initialization notations, the equal sign, the parentheses, and the curly braces. So S2 is initialized with Thornton, S3 is initialized with Unobtainium, S4 is initialized with I'll Be Back. Extra credit if you recognize the science fiction films that Unobtainium and I'll Be Back are from. And now that we've got these things initialized, we're going to start making use of them. Let me put up the second slide of code in my other window. Okay, so now I've got slide 24 in the right-hand window here. The first thing I'm testing with the so-called overloaded equality test operator is whether the string S1 is equal to an empty string. Okay, it's perfectly valid in the C++ standard library's string class to compare the value of a string object with the value of a string literal. And indeed, S1 is empty. S1 is equal to the empty string at this point. So we're going to display that S1 is the empty string. Then we're going to modify S1 by doing an assignment of something new to S1. Now, the plus symbol is concatenation or appending in C++ strings in the same way that it is for Python str objects. So I'm going to say S4 plus, and then here I have a C string, a string literal, space 4 space, and then another plus and S3. So let's see, S4 was I'll be back, and then I have space 4 space, and then S3 is unobtainium. So S1 is going to end up getting I'll be back for unobtainium. I also have an overloaded plus gets operator that works with the string class, and so here I'm adding an exclamation mark to that as well, and then displaying the resulting message. Here's my output. I'll skip back to my Ubuntu window, and there we are. There's that line of output. I'll be back for unobtainium! Exclamation mark. All right, here I am declaring a string object S5 that I'm initializing as S2, okay, Thornton, plus a space. It's perfectly okay to use concatenation for a C++ string object, and then a space, and then I'm also appending a C string, Wilder. The upshot is that S5 is going to contain Thornton space Wilder when this is done. And when I display S5, indeed that's what I get. Thornton Wilder. Okay, Thornton Wilder is a famous author that you've never heard of. You can subscript within a string object using the square bracket subscript notation. The individual chars within the string object are subscripted from 0 up to 1 less than whatever the size of the string or the length of the string is. So S5 sub 0 is going to be the capital T at the beginning of S5. And indeed, that's what we see. Okay, so S5 sub 0 is capital T. Now, I'm getting S5 sub 0 colon space in my output because I literally have a string. I literally have a string literal containing S5 sub 0 colon space. And then I've also displayed a new line character to cause that to appear on a line by itself. I do want to point out a sort of minor thing here, which is you'll notice that in a couple of cases on this slide, I am using the new line character, single quote, \n quote, in my cout statements, whereas in this statement here, I'm using a string containing a new line and a null character for my output. Either one turns out to work because when you use the string literal \n and \0 and a new line and a null, the null character is not displayed. What we end up displaying is all of the characters in the string literal up to but not including the null character. So displaying a string containing a new line character has the same effect as displaying just a new line character. Okay, now let me continue on my right-hand screen, going to slide 25 so we can see the rest of this program. S3 is a string object initialized with unobtainium. I can compare strings, string objects to string literals for order. And what I'm getting here is what's called a lexicographic ordering, approximately a dictionary ordering, except that letter case does matter. Recall that in the ASCII character set, all of the uppercase letters come ahead of all of the lowercase letters. That's not important for this example, but it will be important for our next one. So S3 is unobtainium, and I'm asking, is unobtainium greater than or equal to carbon? Well, this comparison is done on a character-by-character basis. The first character in S3 is little u, and that is greater. That is, it has a greater character code. It comes after little c. So because little u is greater than little c, that's all we need to compare to conclude that the string S3 is greater than or equal to the string carbon. we're going to display, notice here, that I want to display double quote characters, and consequently I'm using single quotes around those double quotes to cause those to be treated as individual double quote characters. So I've got a care double quote and a care double quote. In between those, I'm displaying unobtainium. And then I have a string literal, and in the string literal, notice that I also want to be able to display double quotes. So within the string literal, I have to use the backslash double quote to represent double quote characters within a string literal. In Python, we don't run into this kind of syntactical gymnastics because in Python, we have single quotes or double quotes or triple single quotes or triple double quotes, all as ways of representing string literals. But in C++, we only have double quotes. Double quotes represent string literals. Single quotes represent individual characters. If we want to have a double quote inside of a string literal, then we have to put a backslash in front of that embedded double quote. Okay, so the output from that is going to be, well, since the little u at the beginning of S3 is greater than or equal to the little c at the beginning of carbon, the test is true, and so we get double quote unobtainium double quote followed by space is greater than or equal to carbon in double quotes. And let's see that. And here we are. Okay, so changing back to the remainder of the code on slide 25, our final if decision here is comparing whether S3 is greater than or equal to Wilder. Now, your first instinct might be that unobtainium, U, is not greater than or equal to W, but in fact, because we're dealing with the ASCII character set, capital W does come ahead of little u. That is, little u is greater than or equal to capital W. Consequently, this final cout statement is also executed. We print out double quote unobtainium double quote is greater than or equal to Wilder. And here is that final output line. All right, well, that's just a little taste of the kinds of things that you can do with C++ string objects using symbolic operations. And the output is shown on slide 26. Named operations for string objects include size, which tells you how many chars there are contained within the string. We can also extract a substring. The substring will also be a string object. We can find an individual char or a string or a C string within a string object. We can also erase characters within the string, insert individual characters, strings, or C strings in the midst of strings. So erase and insert should make pretty clear that string objects in C++ are not immutable as str objects are in Python. Now, the current size of a string is the number of characters actually in the string at a given moment. Max size will tell you for your system what the maximum number of characters could possibly be that will fit into a string. And then, if you're dealing with an older library function that requires a C-style string, that is, an array of characters with a null character stuck on the end, you can obtain a C-style string, a C string, from a string object by using the cstr, that is C_str, member function. So here on slides 28 and following, we have an example of this. And I'm going to just go to the output of this program on slide 31, and then we'll talk our way through what's going on in this code. All right, so we are including IOStream and string as before. We are using namespace standard. S1 is a string object initialized with internationalization. I can ask what the size of S1 is, and I get told that there are 20 characters in S1, that is, in internationalization. Now the max size is the maximum size of a string that I could conceivably have within this string class in the library. And s1.maxSize gives me back this outrageously huge number. I think it's about 4.6 quintillion, if I'm not mistaken. All right, so hundreds, thousands, millions, billions, trillions, quadrillions, yes, 4.6 quintillion. Now, the library, in theory, is capable of handling a string that large, but my machine does not have that many bytes on the entire machine. So I'm going to be stuck with whatever I can actually fit in my machine. I have a pretty big machine, but it is only able to handle about 128 gigs, not 4 quintillion bytes. All right. Size t that we're using here as the data type for nat index, nat_idx, is an unsigned data type. I mentioned earlier that we will occasionally come across unsigned data types, often in the case of return values from library functions or arguments that need to be passed to library functions. What the find member function of the string class does is to search for something in that string. In this case, I'm using a C string as the thing I want to search for. Remember that my string in S1 is internationalization. Here is nat within internationalization, and its offset from the beginning is 5 characters. So nat IDX is going to be a 5 in this case. Now, if we look at the documentation for the find member function, we'll see that it returns some type of value called a size t, size_t. Size t is a so-called defined type, and depending on your particular compiler, it will either be the unsigned data type or the unsigned long data type. The point here is that if you're searching for a character or a string within some other string, the result that you get back can't be a negative number. If you get back a valid result, it has got to be either 0 if the string you're looking for is right at the beginning of S1 in this case, or it's got to be greater than 0. Okay, so the documentation tells us that the index we get back from find is of type size t, so we declare it that way. And furthermore, the library tells us that this magical chunk of notation, string : npos, is the value that we will get back from the find member function if there is no match. Now, we can poke around in the string header and poke around in various places to try to find out what the actual value of this thing, string : npos, is for our compiler. But you should not actually do that. What's guaranteed for the string class for all compilers, both existing compilers and future compilers, is that the find member function of the string class returns string : npos if it's unable to find the string that you're looking for or the character that you're looking for. So that is the notation that you should use to compare against to see whether the string you were looking for was not found. In this case, if nat IDX is equal to string : npos, then we'll print out this message that nat was not found. We're also going to return a 1 from main in this case, which we can detect at the shell level to indicate that our program failed in some way. And one last little tidbit here. Recall that the colon operator is the member of operator. Previously we did std : cout to indicate that we were dealing with the cout object that was a member of the std namespace. Here we're dealing with the npos object that is a member of the string class. All right, well, we are going to find nat in internationalization, so this test fails and we drop down to the next part of the code. We're going to get a substring from S1 starting at nat IDX and going for 8 characters. Now let's take a look. Here is where we found nat. Okay, so starting there, we're going to get 8 characters, which is going to be these 8 characters, national. All right, so S2 is a new string object, and it's going to be initialized with national. And sure enough, when we display S2 is a substring, our output is national for S2. Now here I am erasing characters from S2, specifically starting at position 3. I'm erasing 3 characters. Now that's going to be the ION. All right, the first character is at position 0, so 0, 1, 2, 3. Whoops, 3 is the I, followed by 3 characters. Then at position 3, we're going to insert UR. So the effect is that we're going to remove ION first, then we're going to insert UR in place of ION effectively, and our result is that S2 is going to contain natural now instead of national as it did originally. Notice that I can specify a sequence of member function calls on this object S2 in a single statement. Okay, so that concludes this lecture. We now know enough about strings to do a little bit of work with them.